Imagine a shiny modern airliner crisscrossing the globe powered exclusively by clean electricity and fresh air. That's the grand vision of a new generation of jet thrusters making big noise in engineering labs around the world. But is this technology the solution to runaway climate change and fossil fuel dependency, or just a load of hot air? Join us today as we take a metaphorical test flight with the electric plasma jet engine. Before we get stuck into the nitty-gritty of electric plasma jet engines, they truly are just as exciting as the name implies, let's look at how conventional jet engines actually work. Jet fuel, which is usually a kerosene-based petroleum mixture, gets mixed up with compressed air and ignited. This resulting gas heats rapidly, which in turn expands with explosive force. This force is then harnessed to power fans or blasted directly out of the back engine, demonstrating classic jet thrust. Electric plasma jet engines, on the other hand, forego any smelly toxic hydrocarbons. Instead, they generate that crucial propulsive expansion of gas with the help of hot plasma. Plasma, since you ask, is just another state of matter like solid, liquid or gas. Plasma occurs under quite specific circumstances, like at the burning heart of a star or in the air surrounding highly charged phenomena such as lightning bolts. If plasma can be artificially superheated, the theory goes, an engine powered by its expansion could generate enough thrust to fly an aircraft. This essential premise has been experimentally explored by labs in the US and Berlin, but the most promising recent breakthrough happened in, of all places, Wuhan, China. Professor Zhao Tang, a polymath who has worked at Caltech and Bell Labs across various fields from nanotechnology to artificial photosynthesis, was investigating the use of microwaves in synthetic diamond production. In a moment of inspiration, Tang wondered whether a similar technology could be used to generate thrust. To this end, he and his team at the Institute of Technological Sciences at Wuhan University developed a device which ionizes compressed air by running it past electrodes, then forcing it along a specially designed quartz tube. This produces, for starters, a low-temperature plasma. Here comes the clever bit. The tube containing this plasma intersects with a waveguide. That waveguide, a pipe essentially, is carrying magnetron-generated microwaves. That pipe ingeniously gets narrower as it approaches the quartz tube, so the microwaves meet the low-temperature plasma at the narrowest point at their greatest intensity. When that happens, the focused microwaves caused charged particles in the plasma to oscillate wildly, releasing energy and a quite dazzling 1000 degrees Celsius of heat. This in turn creates ta-da! That all-important thrust. Although still in its early stages of development, Tang is optimistic that within a couple of years, his newfangled device might be ready to power drones before hopefully progressing to manned aircraft. So, can we stop drilling for oil already? Not quite yet. One fundamental drawback Tang and his team have yet to overcome is that positively Hadean 1000-degree burn temperature, which is far too hot for any aviation-grade engine housing to endure, not without substantial and probably quite deadly so-called plasma erosion. There's also the not insubstantial question of scale. Under laboratory conditions, Tang's microwave-powered thruster was able to lift a rattly 1-kilogram steel ball over a 24mm diameter tube. In terms of simple force, this could, hypothetically, be directly scaled up to power a usable jet engine. But the airflows would need to be scaled up by a factor of about 15,000. In the world of engineering, what works on a small scale rarely, if ever, works on the grand dimensions of a commercial jet airliner. More intractable than any of those minor gripes, however, is the snag of how to electrically power the device in flight without access to the power grid. Conventional jet fuel, for all its many failings, carries far more energy than batteries can manage at the same weight. As much as 43 times more energy indeed. And weight is a huge deal when you need to get airborne. Tang's experiment created about 28 newtons of thrust per kilowatt of power. The engines on the Airbus A320, for perspective, produce about 220,000 newtons of thrust. That means any comparably roomy aircraft powered by Tang jets would burn more energy than 7,800 kilowatts of juice. Let's say we're using currently available battery technology. You'd need some 570 Tesla Powerwall 2 units for just 1 hour's flight, which isn't very helpful anyway, considering an Airbus A320 can only carry about a third of that many Powerwalls as payload. Tang, like other researchers in the plasma jet field, is waiting on improvements in batteries or compact fusion nuclear reactors to get their brainchild onto the runway. Incidentally, the idea of using small conventional nuclear fission reactors, such as Russian KLT-40s, has been mooted. although the problem of how to radioactively shield passengers, not to mention the catastrophic cost of any crash, makes this plan, shall we say, unlikely. Oh, and even if enough power could be harnessed on a plane, analysts reckon the cabling required to carry all that juice to the plasma engines would be prohibitively heavy, using current technology anyway. Despite lofty claims from the Wuhan team, many analysts believe the technology is inherently flawed, potentially even if the power issues are solved. Steve Barrett, an MIT professor of aerospace engineering, was positively scathing when asked to comment on the research on Twitter last summer. This is wrong in terms of the physics and measurements, he thundered after reading about the Wuhan team's steel ball experiment. What they've essentially done is like heating a stovetop pressure cooker until the valve rattles and called the result thrust. But pressure cookers don't fly. He went on to suggest that adding heat, by microwave or any other method, only works if you compress the air first like a jet engine, requiring mammoth amounts of power. Otherwise, jet engines would not have compressors and you could just ignite a candle and get thrust. Candles don't fly around either. Still, the technology isn't wholly useless. NASA has been using electric plasma engines for some years now. In space, without the friction of atmospheric pressure to overcome, they work just fine energizing xenon plasma. Even with such little oomph, thanks to months and years of constant acceleration in the Gulf of space, they can reach high enough speeds to complete interplanetary missions. Some futurologists have tantalizingly suggested we might see a coming generation of hybrid planes that use plasma jets for cruising in the high atmosphere after fossil fuels do all the heavy lifting on takeoff. Still, suffice it to say that it'll be a good while before this promising green technology gets off the ground. What do you think? Can you imagine jetting on holiday on an electric plasma-powered aircraft anytime soon? Let us know in the comments. And don't forget to subscribe for more high-concept tech content.